Boom. Okay, now we're good. So higher order derivatives here, which means it goes a little bit higher. So first things first is just the whole concept of what happens at the end here. So let's do this here. An example. We're going to go with f of x is equal to. Actually, no, let's do an example. Let's go with x cubed. Make a little chart table for here.
Is that weird one that does the squiggly down?
So just a few things down the road that way. And so we normally, for parabolas, we normally just want to see what happens in the middle because they're nicely tucked around 0. So if we go -3, -2, -1, 0, 1, 2, 3, at least have a good idea what's happening here. And then we go from there. So -3 to the third power. What do you guys say? 27. Okay, that's off the chart already here. Okay. How about -2 to the third power? -8. All right. -1 to the third power. 8. I like that one. 0. 1. 2. 3. Awesome. Okay. So let's convert it to a graph because we want to see a graph for these right here. So 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. We go like this. Boom. So -3, forget it. It's all the way down here, right? -8 is at least about here. -1, 0, +1, +8, and then off and away. We're good. Graph of it looks like it starts from the bottom, goes like this, and goes up like this. What do teachers do when they miss a dot along the graph? Do they have to re-graph the whole entire thing?
No, it's fine. Just move the dot.
We can move the dot over. Even lazier, how about I just make the dot bigger? Boom, got the dot now. That's cool with me. Okay, so that's cool, that's x cubed. So in your mind, you should kind of see this right here. So x squared is this guy. So now we have x cubed, which goes like this. Like that, okay. So then, x to the 4. What would that look like? Let's do another example right over here, just so we can see it. So graph for me. Or again, we just want to see something that's going to happen because of this here. Thank you so much.
And you're alive. What's like that?
And he's gone. Tristan. Tristan.
He's returning a book to someone.
Okay.
He had a geometry book too. I think he's bringing it to this back.
Gotcha. Okay.
Maybe Dr. Reed took, I don't know.
Did we ever take geometry?
Yes,
Apparently.
With Dr.
First
Reed.
Sometime in
semester
life.
last year, it was torture.
I barely remember.
Well, that was the one Amanda hated. She didn't like her teacher.
Okay. Thank you, Tristan. Okay, let's go with it here. So -3 to the 4th power.
I like that number. That's
27. I have calculated.
81.
Wait.
Yeah.
81. Thank you, Abe. Perfect. Oh, hold on. This is so interesting. Hold on. When you have even powers,
It's positive one.
it's
Always
going to
positive.
always be positive. Okay, so that's an interesting thing. 81,
16.
16. That's off the chart.
1.
1.
0. 1.
16, 81.
Okay, so a few things we notice here. That little negative goes away because you have even powers. So off to the side, talk to me, x to the fourth is gonna look kinda like x to the second, is that right?
It's just really.
It's gonna come from the top. It is gonna come, yeah, it's more steep, first of all, and then right over here it becomes more flat, but it's not like a, kinda goes like that. Maybe, we normally draw it like, we normally just draw it really, really, narrow. Just more and more narrow as x is. Okay, so then, guess, x to the fifth. Talk to me, how's that gonna look like?
A really narrow one, like a cube.
Yes, it's gonna be a narrow one of this guy. We good? So, narrow. And goes like that. Okay, so, we wanna talk about something called end behavior. We good? End behavior is what happens at the ends. Or where does it start, where does it end? We can't say start and end, right? Because it goes on forever this way, forever that way, right? So we call it end behavior. As it moves off our chart of 10 and 10, what is it gonna look like? That's kind of what we're looking at. Okay, so you guys talk to me here. And this is cool. So then, without doing a chart,
Oh my word.
Really, 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 really narrow, just really thing like a cube.
And this is called N what?
say again,
It's called N
talk to me, Doug.
what is this concept called again?
Oh, end, E-N-D, end behavior. I'll write it on in just a second. End behavior. X to the 23rd.
It's a big number.
Where does it start? Does it start up high, like x squared x to the fourth, or does it start low, real low?
Low.
It starts low, right? Because it's a odd x spot. We good? We're gonna go like this. We're gonna go like that. Are we good? Pretty convinced that's gonna do that? Okay, so first of all is end behavior. Let's see if we can put using the graphs on this side. Let's make a little chart here. End behavior. X to the even power. X to the even. And we usually like to just draw it. It's going to go like this. Starts high, ends high. We good? So it starts high, ends high. X to the odd power. Starts low, ends low. Are we good there? And the graph of it kind of looks like
Maybe
that.
ends high?
Starts high,
No, after equals the odd power.
oh, and ends. Thank you, Lisa. Boom. Ends high. We good? So that's first thing. First concept of end behavior. And this whole point is just for us to understand these things. That's going to go to the third, to the fourth, to the fifth, to the sixth power. Okay, next. Let me get rid of this one. Boom. Next one is called a leading term test. So let's go back up here. Another example, and we'll put things together here. All right, f of x is equal to negative x squared. What do you guys say here? As far as in behavior is concerned, notice you have a little negative there.
Everything's just gonna be flipped, right?
They're going to be flipped, right? All your negatives are going to turn into positives. You know, good there. And your positives will be turned to negatives. So it just flips everything around. So how about this here? The way it's going to look like, it's going to look like this guy here, only flipped around. So now it actually starts high, ends low.
That just hurts to look at. It feels wrong. I'm so used to seeing that graph, and I don't like that one.
Uh-huh. We're going to learn quite a bit of stuff here. Okay, so in leading term test, how should we write it? So f of x is equal to x to the even, or we should do this here. A x to the even. So that little a value for this one is going to be negative. And we really want to talk about direction. We don't talk about stretching as much. So f of x, a x to the even power. If a is greater than 0, it still looks like this. If a is less than 0, then it flips on itself, goes the other way. And then, again, f of x, ax to the odd power. A is greater than 0, then everything else is the same like we normally do. A is less than 0, then we start high and end low this time. Okay, so there it is. There's our leading term test. I think we're ready. We're ready for the wrap. Tell me if I'm able to erase. Are we good? Can I erase now? At least the example. And I'm going to erase these guys here. So now let's talk about, again, just kind of giving examples here. Let's talk about zeros here. All right, x minus 5 to the second. You should be able to graph at least have an idea real quick here of which way it goes. So 1, 2, 3, 4, 5. True, true. It's going to be a parabola, right? It starts high, ends high. But it's going to go through this little piece right here. So it goes like this. Comes back around, and it hits the 5. Hits the 0, 5 right there. 5, 0 right there. And you know what? I'm not interested really in the fact that it actually hits the 0. I'm interested in the fact that it goes and actually, we call this touches the 0. So let me do one more example here to see if this makes sense as a contrast. draw for me that one. X minus 5 to the third power. That's going to block out just for a second there.
What's that for? Keep it down.
Okay. 1, 2, 3, 4, 5. Is that right? It's gonna go what? Down, up, or up, down? Down, up. Okay. Okay. And I already know the shape of it. Who cares about the shape now? Because I already got it. I'm more interested in the fact that look at this. This guy only touches. Is that right? It only touches the x-intercept. This guy crosses. Talk to me. Anybody have a little theory why that's happening? I don't know. We have, let's see, whenever you square something, doesn't it stay the same sign, right? So it's going to be always positive, positive, right? So when it goes down to 1 squared is 1, 0 squared is 0, and then negative 1 squared, it'll still be 1, right? It doesn't change the sign on it. Here, because it's the third power, we're going to have a sign change, right? Negative 1 to the third power is still negative 1, right? 0 is still 0. The positive one will give you a positive one. So there's a sign change. This guy's called multiplicity. So another one here. Multiplicity. Not the movie. There's a movie called Multiplicity. That's a little different. So it means this. X minus k, that's a k value, to the even power. Ready? And if it's an even power, it's only going to touch. Touches k equals 0. Touches k as function. Touches k as function touches x-axis.
Well, the function doesn't actually touch the x-axis. Does that still apply?
I know, because these guys are here, technically.
Not touch x-axis, but at least with the even ones, because they're always going to be loops, and if they shift down or up at all, their x-intercepts aren't going to be the vertex.
Oh, perfect, yeah, so you can cross, yeah, it can cross through, right? Or this one, if it moved up, let's say we had like a +4 over here, right? Then it would not even touch at all, right? But we're specifically just talking about this little piece right here. Does that make sense? Yeah, just that little piece. And we'll get to why we're talking about those pieces in just a bit. Okay, talk to me here. Let's see, x minus k to the odd power. This guy's going to crosses x, or crosses k as function crosses x-axis. Okay, guys, we got it. This is all the stuff we need to learn today. So in behavior, what does it look like at the ends? leading term, what happens if the number in front is telling us to flip or not to flip, and then multiplicity, how many times it touches or crosses zero. Now, let's build this humongous thing. So finally got to exercise number 1. I'm going to erase the stuff in the middle, just so I can still have the stuff on the sides. Exercise number 1. And lots of steps here, you guys ready? Lots of steps. So, step 1 is find the real zeros of, bless you, the polynomial. That's step 1. Let's see, I guess we can call it A and B. Let's call it A and B so we know where we're at. Step 2. Determine multiplicity. Step 3. You know what? Multiplicity. I guess I'm going to do this here, and we'll tack on turning points right here, and turning points. We'll see those from the graph, and graph. Okay, that's what we need to do. 1.1. Let's start doing the easy one first here. Okay, real quick here. As we get into higher mathematics, the things that we're quite careful about are the x-axis where it crosses the y-axis. Anytime it changes direction, those are the ones that are sort of critical points. Okay, but here we're really going to talk about the x-axis. So if I see a graph like that, x squared plus 7x plus 12, I don't think I need to graph every single point exactly perfectly. We're good? It's just the fact that do we know what the graph of this looks like? Do we know the crucial points here? And this is called higher order polynomial graphing. Good. So let's go for it here. First things first is, can you factor this guy down?
Yeah.
Anybody got an answer here?
X plus 3 times x plus 4.
That's perfect by me. So x plus 3, x plus 4. Love it. And so as we look at this here, we're going to see how we can graph this here. All right, so first things first, find all the real zeros of the polynomial. Where does it hit the x-axis? So if I were to plug in a number for x, what would make this 0? Negative 3 would make it 0. Boom. Over here, what would make that guy 0? Negative 4. Perfect. B. Before we get to B here, let's go turning points. Turning points means this. If f of x is equal to x to the nth degree, has n minus 1 turning points. And we'll do that as we do the graph. That's probably the best to see in the graph.
What exactly is a turning point? Though?
Uh-huh.
So, like, are you saying like where the graph changes direction?
Changes direction, absolutely here. So let me graph like x to the third plus, I'm just going to choose just some random numbers here, plus 1. This guy's going to go like this, and like that. How many times does this change direction from going up to going down?
Twice?
Twice, right? It's going up, right there. Here's my change of direction. Go down, boom, here's my change of direction. and I start going up. We good? I should put it like this, has at most n minus 1 turning points. So, if you have x to the third, you're going to have to change direction twice to get still going up. We're good. It's not going to be able to bend another time. How about x squared? If I were to graph x squared plus, I don't know, 24x minus 15, something like that. Notice this graph is going to go down here, and then come back up. How many turning points do I have? Just one. So it's always one less than the degree value you have. Okay. Now, real quickly, let's go back here. This one right here, you just have the basic x cubed. How many turning points do you have? There are no turning points there, right? It was always been increasing, kept on increasing. So there's a little bit more we can add to that, but at least you know that at most it's going to have n minus 1. You can't have more turns than you have degrees. Okay, so determine multiplicity. Multiplicity is this little exponent hanging right over here.
So what is add? Or is that h or add to the turning point?
N is the degree, so in this case it's the second power. So we have
what you're saying is that it cannot have more than one turning point then? If it's
correct.
n, and then the turning point is just like the third.
It's the change of direction from going up to going down, or from going down to going up.
So then like x third cannot have more than 2 turning points?
X to the third, yep, can't have more than that. It can have 0, right? And it can have 2, but not more than that.
Is it even possible for x to the third to have 2 turning points? Like
Okay.
in theory it's possible, but what would it look like?
Yeah, x to the third, you have 2 right here. Here's 1, here's 2. Notice x to the third can't have 1 turning point, right? Because x to the third has to start low and end high. So if it changes direction once, it's going to not be at x to the third. Okay, are we good? Man, guys, you guys did a lot today. At least we learned a lot today here about this stuff. B, so let's go. Determine multiplicity. Multiplicity at multiplicity of 1 at x is equal to -3. Multiplicity of 1 at x is equal to -4. And then off to the side, you could just put, it's actually better just to put odd, because you don't care about the number, you don't care about what power it is, you care about the fact it's even or odd, because of this guy. So multiplicity of 1 at x is equal to -4. Okay, and then we got ourselves turning points. At most 1. We're going to have at most 1 turning point for this guy. Dylan?
So if you're saying the multiplicity of 1 is equal to odd, then is multiplicity of 2 the same thing as even, or what is the?
Yes.
Oh, that's a different.
It's this guy here. Okay, let's put this all together. We good? Can I start erasing stuff though? Can I erase this stuff right here? Okay. You guys remember here, back to Algebra 1 days. Remember in Algebra 1, did you guys graph x to the second power? You guys do graphing?
Yeah.
I don't really remember what we grabbed.
Everyone did it.
Except for me, I don't like graphing.
How do you not?
I never said I loved it. I just don't hate it.
Okay.
If you don't
Fair enough.
dress up for dislike.
All right, guys, let's put this together. Again, this is the Algebra 2 way of graphing. I don't care about other stuff except for when does it hit the y-axis, when does it hit the x-axis, and where does it approximately turn. That's it. So it hits the y-axis at, anybody? Where does it hit the y-axis?
Well,
at 12. If that's a 0 and that's a 0, only thing remaining is 12. So you can put over here if you like. You can put f of 0 equals 12. So I'm going to just plot 12 like right up here. Zeros are at -3. So I'm going 1, 2, 3, 4, 5, whatever. I got a 0 here. I got a 0 here. I know, and one more thing. I know in behavior, and we put little arrows at the end. I know this is x squared with a positive in front of it. We good? So I know in behavior is going to be like this. I know it has to start high and end high. We good? Okay, based upon those clues, x-intercept, y-intercept, turning points, and end behavior, can you guys make a graph of this guy? Yeah, if it starts high, this is going to be very shallow, right? It's going to go like this. So I'm going to go like this, maybe, turning around, like that. And then I'm going to extend this out. I'm going to erase these because these were just for me to start with.
So that's fine for when like if something on the test says to graph a problem, that's acceptable.
That's it right there. I got the important stuff out of there. Okay. Let's do another one here, just to sort of get going here. I'm going to erase the board completely here. Let me erase this side now. So a little bit of work to do, really just a factor. And then really just putting everything together here. And again, I remember in Algebra 1, did you guys do a table, right? The table for like the longest time ever, right? Then you plotted the dots, right? And then for parabolas, you needed at least 5, maybe sometimes 7 dots. And then you connected the dots together, and you're like, woohoo, I'm done, right? So again, this is kind of like the next version. And 1.2 is what we're going to graph. Dylan, question?
This is a question about the last problem. So I thought that multiplicity was determined by like the what the x is squared or cubed by, but in that problem it's x squared and the multiplicity is odd. So what determines the multiplicity?
Perfect, good question here. The multiplicity is this little exponent right here. And it's exponent on the factored form.
Okay. But then if it was like a perfect a square, would it have been 2 and an even? Like if it was x plus 5 squared, would it have been multiplicity 2 and an even?
2 and even, yeah. Absolutely. All right. Boom, boom, boom. I like this one here. So how about this? I'm going to change the variable for you guys for t. And t to the 3rd power minus 4t squared plus 14. I'm going to erase this right here. And the graph. Okay. Let's go for it. All yours. See if you can do it before me. In fact, give you guys a little bit of time. I'm going to roam the room for a little bit and see if you guys can go for it. A little bit lower here. Factor it down first. All right, after factoring down, if you have the same exact term, right? We're trying to do exponents here. If it is the same exact term, you can write it once, and then put the exponent. See, I got a couple of things here. First things first, I see a t in all 3 terms, don't I? There's a t in all 3 terms, so I'm going to take the t out. You're left with t squared minus 4t plus 4. First step. Second step is, that is a perfect square trinomial. And I think most people got to here already. Cool, so let's do our little investigation here. Real zeros are x is equal to 2. B. Waiting for someone to say, Mr. Hungy, Mr. Hungy.
There's two terms and nothing has two different multiplicities. Because t minus 2 squared multiplicity of 2 is even, but t would only multiplicity of 1.
What do you mean by T?
Return to x.
I don't know why we turned to X. I don't know. Is there another 0? That's the question. Abe says T is equal to 2, correct?
There's no zero.
Ah, cool.
Oh, wait, but you have the term outside the.
I got this guy. Isn't this guy? It's not T minus anything, right? It's not T minus 1. So that would become just a 0. We're good? So I got T is equal to 0 and, T is equal to 2 and T is equal to 0. Two different zeros here. Alright, multiplicity of, let's put exponents on here. I'm gonna put a little 1 right here, right? Multiplicity of 1 at t is equal to 0, and that is an odd multiplicity. Multiplicity of 2 at t is equal to 2, and that is even. Turning points. At most, how many?
2.
2. At most 2. Perfect. Okay. Then I'm going to let you guys try this yourself here. Can you guys graph this? The only thing I'm going to tell you is think about the y-intercept. Good. Second of all, think about in behavior of this leading term. So let you guys do that. Start, is that okay? Start. So first things first is going back up to the original function. Let's do this here. In behavior. For the fun of it, let's do by rows here. So Isabel or Annette, in behavior. Low, high, high, low. What are we talking about?
Start low and high.
Start low and high, okay. Boom, boom. Row 2, Dylan Landon, talk to me, give me the y-intercept.
Yeah, 4.
4. I think it'd be 0, right? As you plug in a 0 to each of the terms, all the terms have t's in them, so all of them are going to turn to 0. So that's cool. In fact, that's one of the x's already, huh? Or one of the zeros that I have. Boom. So zeros now. I got a 0 at 0. I have another 0 at 2. Like this. Boom. And then sometimes I make students write a T if it's going to touch, and write a C if it's going to cross. So row 3. At 0, crosses or touches?
Cross.
Multiplicity of 1 at 0, and it crosses. Are we good? Row 3, again, at 2. Crosses or touches?
She's gonna touch this time, right?
Just touches, right? And if you want to put a little T there, that's fine, just to say that that's cool. I think we're ready for graph. So I'm going to go, starts low. It has to cross here, only touch here. So I'm thinking like this, probably something like this. It's going to come up, crosses. Somehow it has to turn around. Turns back around, just touches. Oh, it actually gets to my arrow here. Boom. Are we good? That's so cool. I think it's cool because we get to graph stuff like t to the 3rd power without doing like this whole humongous. Could you imagine our little table? If we did it by table, we'd still be here for a long time. Okay, one more problem. One more problem. Still the same stuff. I'm going to add one more, so this would be 2. Change it up a little bit here, guys. Ready? Exercise 2. I'm going to add one more little piece to it here. I could have added it earlier here. So D, this one's going to be, I should have just, because we did it the same way. In behavior, tell me in behavior, and then D is for graphing. It just looks a little different as you do it up here. So here's 2.1. Here's what I need. Type x is equal to negative 1/4. X minus 2 second. I could change it up as well. How about that for fun stuff? Let's get to graph that. What degree is that, anyways?
Second, right?
Let's see, I think you have 2nd degree here already, right? If you were to multiply this all out, that would be 2nd degree,
Would that be
Oh,
4th
okay.
degree or 4th?
3rd, 4th. That's 4th degree polynomial. So in your mind, I'm thinking this guy. The number in front of it, careful here, right? So we got a few things to go off of. So first things first, A, we did need to do, give me all the zeros of this polynomial.
2, negative 2, 1.
Awesome. Multiplicity of 2 at x equals 2, and that is even. Multiplicity of 1 at x equals negative 2 odd. Multiplicity of 1 at x is equal to 1 odd. And we've got turning points, right? Turning points at most 3 at most. Okay. For C, we just want to really specify in behavior here. Let's talk to me. Starts low, in low, low high, high low, or high high.
Starts low, ends low, because it's negative.
Okay, are we good there? It's low, low. So somehow, we should not graph the whole entire thing. So what we normally do, we just go like this.
How do you figure out the low though?
So remember from earlier on today, anything with an even power, it's going to go like this,
Oh, that's a negative front. Okay.
negative front. So here's your in behavior. We can just naturally just do 2 arrows at the end. Okay, due to time here, let's jam with the graph of this guy. So, I got zeros at 1, 2, 1, 2. I can do 3 and 3. So at negative 2 I got a 0, at positive 2 I got a 0, and at negative 1 I have a 0. At positive 2, it's even, so it just touches. This is a cross and a cross. We're good? End behavior is down low. We're going to finish down low eventually. And the only thing for these guys, because these guys are already in factored form, can you quickly find out for me what is the y-intercept? So 0 goes here, a 0 goes there, a 0 goes there.
-1. Wait, no.
0 minus 2 is negative 2. Squared would be 4. Are we good there? 0 plugged in here is 0. That's going to be a 2. And 0 plugged in here would be, I need that.
Be 7. No, it's multiplication.
Multiplication all the way across.
Negative 2.
Negative 8 times
No,
2
just
is
2.
1/4.
Just 2?
2, yeah.
Just 2, okay. Now let's see if it makes sense. Because what's going to happen when you guys graph it, you guys maybe will have this dot down here and like, oh, hold on, it doesn't make sense based upon the turning point, the y-axis, what happened. That's kind of what you want. Okay, so I'm going to graph it. Cross, cross.
Wait, does this work?
Yeah, does this work?
Yeah.
No. I don't think it does.
Wait. No, I was gonna say positive 1, not negative 1. For the x-intercept.
All right, that's cool. Okay, so this one here was in the wrong place. It should have been here for the cross. Does that make sense now?
Yeah.
Yeah, and that one works, because, yeah.
Okay, perfect. And that just might have it on the homework. So let's go. Boom, cross. Has to hit here, cross. It has to touch here, so that means it has to turn around. Just to do a quick turnaround. Touch, and then come back down. How many turning points do we use? 3, huh? There's 1, there's 2, and then actually that guy was 3 with the touch. And now it makes sense. We good? Boom. Okay. Guys, that's awesome. We just learned how to graph a crazy x to the 4th degree polynomial. All right, you guys have enough now to do 2.2.